Uh, then let's start today's class. Today we want to discuss about the bifurcation, various kinds of bifurcation. So let's first go back toward this. Then, so far what we have learned. So we have learned that what is fixed point, what is okay. So far we have learned that what is fixed point, then we can calculate the fixed point now. And another thing we have done, we generalize the definition of fixed point, and we know what is the closed periodic orbit means. Closed periodic orbit means. Then we extend or we can refine the concept of fixed point or the closed orbit to the point of stability. What does stability means? What does stability means? We have seen that if a fixed point is stable, then we can say what does stability means for a system. And we have seen that if a fixed point is stable, then we can safely say that the system's ultimate fate will be that fixed point, or system's ultimate fate will be the state corresponding to the fixed point. We have raised that one. So, and we have defined that the stability. So a fixed point can be stable, a fixed point can be stable or can be unstable, depending suppose fixed point is x star, and my map is f. Suppose that xt plus 1 will be f of xt, then stable fixed point means modulus of f at x star will be f prime less than 1. That means if I derivative this function, what f prime x means d dx of f of x, and if I put the value of x star, we will get the f prime x star. And if f prime x star greater than 1, then we will call the fixed point unstable. Now unstable, so we have altogether means 1 point. So what does corresponding to, or maybe you can say we do not means, so what does if f prime x become 1, what is that? So what does mean f x equal to 1, f prime x equal to 1? So this means at that point, means if since we know this f prime means, since if I go back to our previous class, so then it will be clearer. So if we go back to our previous class, we can see here the equation of the tangent. So if we go back here, so we can get, this is the equation of tangent. If I draw a tangent in P, suppose I have this kind of map and I want to draw a tangent at P at this point. So if I draw a tangent, the slope of the tangent will be f prime P. So it's nothing but the slope of the tangent at that point. So f prime x means it will become the slope of the tangent at that point will become 1. So how does it look like? Let's see it. Suppose this is my, and does not look like that, maybe. Okay, I'll graphically I will show you later. Let's see first what does it mean. So it means that at this point, that when the slope become just equal to identity, slope becomes identity, that means the tangent and identical line y equal to x line will become same. That means, so after when f prime x will become greater than 1 or less than 1, then only you can see there is possibility of creation another fixed points. So this is the point, is called the point of bifurcation. Point of bifurcation. So if I give you that example that we know, then it will be very much clear. So suppose that we have a equation, logistic equation xt plus 1. So means the motivation of to study the bifurcation is the mathematical term, and when we will go through this class, you will see that this bifurcation means that if I change, bifurcation means if I change some parameter a little bit, if I change some parameter very little, the system behavior will be different altogether. Let me give you an example from our discrete population growth model. So suppose our population growth equation is xt plus 1 r xt 1 minus xt. Now let's calculate its fixed point. So at fixed point, we know that the definition of the fixed point, we know that this fixed point will remain fixed under the action of f. That means x star will become r x star 1 minus x star. If I solve this equation, I will get x star minus r x star 1 minus x star equal to 0. So it will become x star equal to 0, or 1 minus r 1 minus x star will become 0. This means 1 minus x star will become 1 by r. So x star will become 1 minus 1 by r. So equivalent we can write r minus 1 by r. Now you see here that and let's see, these are the two fixed points. Okay, so these are the two fixed points. So let's calculate the f prime x star at x star equal to 0. So f prime x at x star equal to 0. So what it will be? So if I derivative this function, I will get r into 1 minus 2x. So if I put x equal to 0, so at x equal to 0, then I will get r. So you get the slope at x star equal to 0. You get one thing, the slope of x star equal to 0 is equal to r. So we know that if r less than 1, we can say, or we know from our mathematical theorem, that if r is less than 1, then from mathematical theorem we know that if f prime x at x star equal to 0 equal to r will become less than 1, then we can say that this fixed point, that x star equal to 0, this fixed point will become stable. So what does it mean? It means if the report r, we know that r means 1 plus mu equal to r. So mu is the growth rate or per capita reproduction rate. If I go back to our previous where we have developed the model, we know that 1 plus mu, and mu is the per capita growth rate. Per individual, how much offspring they will produce in this generation. So that will be mu. So this means if this become less than 1, so that means 1 plus mu become less than 1. It means mu less than 1 minus 1c. So it says that if the per capita reproduction rate becomes negative, then the population will go towards x star equal to 0, then will go towards extinction. So that is quite true, because we know that if the per capita reproduction rate becomes sometimes negative, then automatically we know that population will decrease as time goes on. At times passing by, the population will be decreasing. So you see that means these r, when r less than 1, the population actually going towards the extinction. Now the point comes, if I increase the r, means if somehow if I give them enough resource, that's when the r becomes increasing. Now when it hit this point f prime x at x star equal to 0, suppose r becomes 1. Now you see, when r becomes 1, mu becomes 0. Now if I change a little bit of r, suppose if I make the r increase by 0.0001, now you see that one thing, that then f prime x at x equal to 0 will become greater than 1. And if it become greater than 1, then we know that this fixed point will become, that x star 0 will become unstable. We can say that then the population will not, by any means, cannot go toward extinction, because it, by some means, it will always avoid the extinction. So you see that this is called the bifurcation. So when I increase the r, and when it reaches 1, then when just after r equal to 1, so if I increase a little bit, the x star equal to 0, the extinction can become unstable, means the system will never hit the extinction. System will not going to extinct, or system will going to extinct depending on the r. Whether r is, if I increase the r little bit, increase the r little bit, or if I decrease the r little bit, then the system of the population actually change drastically from extinction to non-extinction. If r become less than 1, the whole population will be extinct. So that is a very unfortunate thing for the population. But if the somehow r become greater than 1, then it can completely avoid the extinction. So that is called the bifurcation. And r equal to 1, where this sensitivity occurs in the parameter at which range, so that is r equal to 1. And if you see when what is the value of the slope at that point become 1. So then that's why this is called the bifurcation point. R equal to 1 is called bifurcation point. It is called bifurcation since if I r increase, that's it. Now another thing you can see from the expression of the fixed point. What is the other fixed point? So if you see x star to r minus 1 by r, this is the other fixed point other than x equal to 0. X star equal to 0 is one fixed point, and the second fixed point is x star equal to r minus 1. Now you see, if r less than 1, then what will be the value of x star? X star will be less than 0, and since the population state can't be less than 1, because less than minus 1, less than 0, because negative, what does means negative number of individuals are there in the population, that there is no meaning of that. So that means for r less than 1, this fixed point is not there in the physical range. So if I draw it physically, it means, so suppose that this is the identical line, and suppose this is r equal to, this is not an identical line, suppose let's see this. So identical line will be this, not this. Identical line will be this sum, y equal to x, and this will be the tangent tau x at x equal to 0. And in case of identical line, you can see here we can actually tell that the slope of this tangent is higher than this. So that means here the slope means f prime x is greater than 1. You see that when f prime x will be greater than 1, there will be two fixed points, because this identical line crosses cross sect or cut this fx two times. One is 0 and other is any positive point. Now think about this case. My drawing is now think about these fx. So here you see this is the tangent tau x, and you see the slope of this tangent, slope of the tangent is less than 1. So for slope less than 1, you see there is only one fixed point, and when slope become equal to 1, these two will become exactly same. So first let me draw this. This is suppose the identical line. Suppose this is become that now, and this is the slope. So you see the two slope and identical line is become same at r equal to 1, and if I increase further, you can see that there is a increase further, there is creation of a new fixed point which is here. So this is called the bifurcation because of the change of parameter. So this is only one kind of bifurcation, and this bifurcation is called transcritical bifurcation. This is called transcritical bifurcation. Let me tell you what in general transcritical bifurcation. So in transcritical bifurcation, what happens? So suppose that there are two fixed points. One is stable at suppose x equal to 0, and if you let us calculate then I can say here what is the stability at x star equal to r minus 1 by r when less than 1. So f prime x is r into 1 minus 2x. So r into 1 minus 2 into r minus 1, okay, 1 minus r, suppose 1 minus r by r. So it will be r 1 minus, okay, it will become r minus 2 plus 2r by r. So this is 2r minus 2, so 2r minus 1. So you see, if r less than 1, then this actually f prime x, modulus of f prime x, you will find that it will always become greater than 1. So that means x0 is stable, and another fixed point, let's just become x star equal to 1 minus r by r. This is stable and this is unstable for r less than 1. Now if I change the r through this point r equal to 1 and become r greater than 1, then you see the stability of these two fixed points changes. So the stability now become this r equal to 0, x star equal to 0 become unstable, x star equal to 0 unstable, and this point x star okay, here I am right, I think right, 1 minus r by, let's see, okay, x star is r minus 1 by 1, so that's why I am not getting the correct expression. This is r minus 1 by r, so r minus 2r plus 2 plus, so it will become minus 2r. When r greater than 1, you will find that this will x star equal to r minus 1 by r becomes stable. So through this point, if I my parameter goes from this point, so you will find that the stability of these 2 points changes between itself. So this is called the transcritical bifurcation. So is it clear, Subhusaji? Means I know this is a mathematical things, but to means in case of the study of dynamical system, these terminologies are very important, because you will often found in the textbook or any other context that these kinds of bifurcation appears everywhere. So you will find that everywhere this kind of bifurcation is there. So this is called the transcritical bifurcation. So in transcritical bifurcation, the stability of the stable and unstable fixed point changes. This is one kind of fixed point. So if you find something, if you not understand anything, just stop me and ask me at that point. Okay. Now second case of bifurcation is called, which is very important bifurcation, is called saddle node bifurcation. Saddle node bifurcation. Now here comes an interesting story. So as in the previous case, what we have seen, in the previous case what we have seen, that if I write the equation in terms of like this, in okay, maybe not. T plus 1 is I into T 1 minus T by K. So this was our previous population growth model. And what was our assumptions? The first assumption was that when n near to 0, that means if there are very few individuals are there to consume the resource, the growth rate will be exponential. And if growth rate is higher, if n becomes some constant k, the carrying capacity, the growth rate will become 0. And if n become greater than k, the growth rate will become negative, because the more individuals will be there, the competition for the resource will increases, and they will get less amount of resource, and the growth rate will be less. So this was good enough. But in 1930, one individual's name Ali, in 1930, that Ali through some experiment found that in goldfishes, so it is not quite true that when n is less, means if this model's assumptions is perfectly alright for the goldfishes, then according to this means if n less than, if the number of goldfish is, means suppose he actually found that the survival of a single goldfish is lesser than of a bunch of, means if there are more than one goldfish. So he found that the survival of a single goldfish is always lesser than when in a jar there are more goldfishes are there. So these somehow contradict our assumption, because here we assume that as n increases, the competition for the resource increases. That's how they will get lesser amount of resource now, and that's why their reproduction rate will decrease. But what Ali observed, that contradicts his assumption. So he found that the single individual survive less. So then concept comes up in her mind, which is called the Ali effect. So it is for some species it is quite not right that when n become very less, their survival rate will be higher. It is quite opposite that for the survivability of that in species, there needs some cooperation, there needs some other more individuals to survive that population. Suppose for example for an ant colony. So in ant colony, you will see the all worker ant will do the work for the colony and colony survival, such as foraging, foraging, brood caring, and that fighting for their nest. So these things these things actually do by the worker of the ant colony. Now if you suppose that there are only one individuals are there, so the survival of that colony maybe means you provided a lot of resource to that that colony, ant colony, but what happens in the ant colony, because they are cooperative individuals, so due to lack of cooperation, if one individual is there, no cooperation will be there, so they can't survive. So these things hit us towards one thing that is called alley effect, which says that the population model should not be like this. Population model should be adding by for modeling ant colony, or for modeling ant colony or this goldfish population, we need this kind of population growth model where it says so nt minus some a. So it says that if I see here where nt less than means n close to 0, they will see the growth rate will be nt plus 1 nt, or as time goes, not this square, right? So you see this will become nt plus 1, this will be approximately r nt minus e. So you see here one interesting thing once we should notice here, that the growth rate, so this is growth rate, per capita growth rate, suppose this is per capita, this is per capita growth rate, let me write it properly, nt plus 1 minus nt by nt. If I do this, what we will find? Nt minus r nt square by k nt minus 1 is nt. If I divided by nt, so what we will find? R minus r nt by k into nt minus, so both minus nt straight, so nt minus k minus 1. So this kind of thing. So you will find that when r is close to 0, you will find that this is become the rate. Actually this is not quite true, I think this is not true. Suppose that per capita growth rate will be, so how much they generate means how much they increase, what is the number of increment. So this will be, so when nt plus 1 by nt and nt less than 0, limit 0, then it will closely become, because this term will be cancelled only if I take this term, so r into nt minus e. Since this term is very small, we neglect this term, but we can't neglect this term because it is only nt, and nt by a larger quantity, so this become very small. So approximately I means we in relative to r we can't take this, so that's why we approximate it at nt goes to 0, but we can't take out this altogether. So you see here one thing, so you see that previously we have found that when nt is tends to 0, the growth rate always constant r, but here not constant. If you find that the growth rate will be greater than 0, or you will say the population actually growing if and only if that if okay, there I think there is minus nt will be there. Okay, let me minus nt, so this will be 1, here is minus 1, here is minus 1. So if r greater than 0, not r greater than 0, so growth rate, when the growth rate will be greater than 0, growth rate, suppose this is growth rate g will be greater than 0 if r nt minus a minus 1 greater than 0, means nt if greater than 1 by r plus a. So you see that if this nt, the number of individuals, is greater than, this is, I think this is not quite right, so it should be not greater than 0, because we know that this is should not greater than 0, so it should be greater than 1. 0 does not mean anything, so it should be greater than 1. So it says, well, 0, I confused here a little bit, I don't know, but it says that when nt greater than a plus 1 by r, then we can say that population is actually growing. Population is growing. So you see that if I have initially less than a plus 1 by r number of individuals, then it basically says there will be no cooperation. Suppose in a ant colony there are, okay, so if suppose that in an ant colony there are lesser number of individuals, lesser than some amount, then there will be not enough individual to take care of this their brood and their whole colony, and they will not survive at all. So this says that if nt lesser than a plus 1 by r, then the whole population is going to extinction, and if nt become greater than 1 by a plus 1 by r, this says, so that means to grow a population or to survive a population, we need at least a number of individuals present there. So this is called the alley effect. So is it clear, Subhusaji? So how we modify it? So from, if it is clear, then I will continue it to make you understand what a saddle node bifurcation is from here, from this example. Okay. Then from here what we will say, there is another thing, means this is called the, so if I, okay, moment. So from here what we will study, the transcritical bifurcation. So now what is our fixed points? Let's calculate first fixed points. So nt will be, suppose if x star n star into r n star 1 minus n star by k n star minus a. So one fixed point is n star is 0, that means extinction. Another fixed point will be 1 2r 1 minus n star k 1 by r. So this will be n star minus a minus n star square by k minus plus a n star by k. So this is n star square by k minus, or maybe a minus n square. This is, so will be minus 1 plus a by k into n star plus a minus 1 by r is 0. Let me recheck it. So 1 by r, so this will be n star minus a, this is n, this minus n star by k, and this is plus a n star by k. So a plus q a by k n star plus a minus plus a plus 1 by r. So this is, if I solve it, n star will be plus 1 plus a by k root over b square plus 4a into c by 2 by k. So this kind of thing will get. Okay, this there is a minus. What I missed, there will be a minus. So there will be 3 fixed points. So one is n star equal to 0, and other thing is these two. Now if you see that when you see that this n, this a, there is a call there. So this means there are 3 fixed points for general a, for there are 3 fixed points. Now depending upon the value of a, you will find that this fixed point stability changes. So now the question comes, when these, suppose, okay, now when if in this a and k become equal, the first case is when a and equal to k. So then you will find that when a equal to k, you will found that the both the fixed point will become 0. Okay, let me calculate it, then it will be clearer. So actually it's become quite complicated. If let me first draw it, then pictorially it is clearer. So it basically means this function which we are mapping. So this function is basically this type of thing. So this is our function which is map, and this is nt. So you see that our map will become 0 at nt equal to 0, nt equal to a, nt equal to k, and these fixed points are these points are basically that it is 0, this is a, and this is k. Now if I draw the identical line, suppose this is identical line, this is our identical line, this is identical line, this is identical line. Now so I have chose such value of a for which you see that supposedly, can you tell me from this graph what is the fixed point here? Means if you can guess here, what is the fixed point here? We know where this identical line and this black line cut each other, we say that a fixed point. So what is the fixed point here? So this is 0. So you see here only one fixed point is there. So this is corresponding to this. This is a fixed point. Now there are no other fixed point. Now if I choose a and k in such a way, or maybe a such a way, so then what it will become? If I choose a in such a way, that it, suppose this is the identical line, this would okay. Now this is my identical line. Now you see here there are two fixed points. One is this one and another is this one. This is a, this is k, and this is 0. So if I choose my coefficient k in such a way that here only two fixed points are there, one fixed point corresponding to this and other fixed point corresponding to this. Now suppose I always consider r greater than 1. If r greater than 1, you will find that this fixed point is stable, or this fixed point is or whatever r we choose, you will find that this fixed point is stable and this fixed point is unstable. This fixed point suppose is stable and this fixed point is unstable. Now if I decrease a further, what you will find that this kind of graph, and where you will see that identical line, this is identical line, this is k, this is a, this is 0, identical line cross cut this black line in 2 points. First this stability remain same. If it was previously unstable, it remain unstable, and it is previously stable, it remain stable. No change of stability change here. But here you find that there are two fixed point will appear out of nowhere. So one fixed point is this. So this fixed point was not there. So here you find that only touches here. So only one fixed point become. So this is the point of bifurcation. This is the point of bifurcation. So out of nowhere, one fixed point generated. Now if I decrease the values of a further, you will find that there are two fixed points appear. One is here and another will be this point. So you see that out of nowhere another fixed point generated. So this fixed point is stable and this fixed point become unstable. So how can I tell this is the case? So this is called the flow diagram. So So if suppose this is the stable one, so this is the stable one, or maybe this is the then becomes unstable, so unstable one. So this means, or maybe this is become, this remains stable, suppose that this remains stable, this remains stable. So here this fixed point will attract here, and here also they will attract all the initial condition neighborhood of this point, they will attract, so they will go in direction. And here if it is become stable, so then also here also it attract all the initial condition which is near about this, and automatically you want to maintain the flow. You can't create such like a structure, so it automatically it will repel all the initial condition which will be neighborhood of this, so this become unstable. So you see, out of nowhere two fixed point is created. One is unstable and another is stable. So, and in place of the stable, if it is become unstable, stable become unstable, it become unstable, then this flow will become this, and then you will find that this point will also become unstable and this will become stable. Why? This will repel this condition in this way, this will also repel the condition, the initial conditions, initial trajectory in this way, and you find that all the trajectory will come towards this point, this fixed point. So if find that, you will find that if I change it, what is the stability of this point doesn't matter, or this point doesn't matter, automatically two new fixed point will create it. Or if I go in reverse direction, suppose if I increase A in such a manner that these two fixed point touches each other, means if I increase A, you will see that this will decrease, and at some point these two fixed point will touch each other and annihilate the two fixed point each other, and that's how. And after, if I increase a little bit further, this fixed point will move away. This kind of bifurcation is called the saddle node bifurcation, or in case of map this is called blue sky bifurcation. Out of blue two fixed point is generated, that's why it is called the blue sky bifurcation. That's all. Is it clear, Subhutaji? Means I know these are quite means not easy thing to grasp. Okay. Distorted. Oh. Okay, I will try, but means if I say you, and that things means now I am in Isaac Kolkata, so whenever I will go back, but it took a lot of time, is I will going back to IIT Kanpur at 24th of November. So that means after that, since here the I don't know, then the Wi-Fi is very poor, and my mobile network is also very poor. So I don't know how much I can do in this thing, but I will try. I will definitely try. So yeah. Yeah, it is my part of PhD, but I am here collaborating with this. I am currently I am doing a research on the, if you know about something that the traffic system of ant. If you search in Google, you will find that famous paradox. It is called Brace's paradox. Braess apostrophe S. So this is called a paradox. So means researchers have found that human always fall for this paradox. Now it is quite well known in literature that the ants are very much capable of maintaining a very good traffic management system. So my PhD work is, now the project I am working on is that whether or not these ants are capable of avoiding this kind of paradox. And we know that the answer means humans are not naive, but in comparison to humans, ants are so naive, means their cognitive capability is limited. So my hypothesis is, out of randomness, if they do something, so I am trying to find the things here. So that's all my research work. Ah, then next Friday. So I am telling you what we will do. So in the next Friday, I will tell about another two bifurcation, because you see that these means wherever, means if you want to stay in the modeling paradigm, so you will find this bifurcation very often. So one is Pitford bifurcation. Another thing is period doubling bifurcation. And why I am interested in this period doubling bifurcation, you will see that this is the one route, means there are another two routes, but this is the most famous route to the chaos, means from logistic equation. When we will see that how the chaos is appearing to the system, you will find that by period doubling, the chaos is actually come from nowhere. So since we are after the chaos, so this is important. So that's why, and I think at the end of the November, I think I can means I can complete the whole courses, means whole of this series, that after 3 or 4 classes I will, means you will actually can grasp the definition of the chaos, what is the meanings of this sensitive dependence of the initial condition, and what is the meaning of transitivity. So that's all. So see you in the next class. Okay.